Hello, good afternoon. Welcome to the class ECE317, the digital signal processing 1. This video is recorded for the class of the 9th week, Wednesday's class. I will say, I'm better. I'm better now. I'm better enough. Can record a video for the class, and tomorrow I will see the doctor, and if everything goes good, I can go back to campus on Friday. So most possibly these times I think it should be this Friday we can meet in the campus in the classroom. Alright, and today this class I will go over the midterm exams. Right, we just had the midterm exam this Monday, and today let's go over the problems. This is the problem, this is the solution. Okay, this is the problem, right? Yeah, midterm 1, digital signal processing 1, midterm. Okay, the first problem, we have 3 different kind of systems, and we want to check which kind of systems are these 3. Okay, we look one by one. Here are the answers. So the first system, the output is a combine of input with x of n, x of n minus 1, and x of n minus 2, each with a constant coefficient in front of it, and add or subtract them together. So actually this is a typical LTI system, right? This LTI system is it's just a typical FIR LTI systems, right? So we know it will be linear time invariant. Okay. And for causal, you check the time. Here we have n and n minus 1 and n minus 2. So all these 3x, they are current x and some early x, right? Previous x, right? So it is causal. The system is causal. And for stability, the output is a combine of 3 values from the input, each with 1.6, 2, and 1.3. So you have a limit, right? You have a bound. It's at most like 2 to at most 6, right? Less than 6. You add these numbers, 3 numbers together, you will have 2, 4 to 9, right? Yeah, less than 6 times. So if input has a bound m, the output you also have a bound. The bound will be no more than 6 of the input's bound, right? 6 times of the bound of the input. That will be the bound of the output. So this is also a stable system. And last one is memoryless. Memoryless only happen when the output side depending only on the x of n itself. But now we have x of n minus 1 and x of n minus 2, so it is not memoryless. So this is for A. And for B, the output is input with we have a double in the times 2n, x of 2n, right? So this one, of course, it is stable because the bound of input will be the same bound, right? The output will have the same bound with the input. Like if input is no more than 10, then the output will have same range of value, no more than 10. Depending what is the input. If input is bounded, the output must be bounded, right? It is just x, but the time will only use 2n times, so that means the output only use those even index. The time index they are even. So here the output side here we only have like a 0 to 4, right? 2n, right? 2n. that is stable. And then cautious, no, because like if n is 1, this will be x of 2. So at time 1, the output value depending the x of 2, that is a future value, right? So this is not cautious one. It's not a cautious one. And the linear, yes, yeah. If right, this is just x itself, so of course it's linear. If you add in the input, then output is also you need to add them together. If you have a scale times in front of that x, and output were times the same scale. So this is a linear. And the time invariant, no. The time invariant means if input shifted by certain distance, certain time, shifted by certain time like a delay, then output will shift the same time interval. But now you see the input is n, output is 2n. It's 2n, the double. So if input is shifted by certain time, then output was shifted by double or half, right? Only half, because here's a times 2. Yeah, it's a half times. Yeah, you can check. For example, you use input, you just use any input, you use the delta as input, then what will be output? If you shifted the delta by like 1 or 2, then the output will be also a shifted one. Shifted how much? That will be different with the input, because here you have 2 times on the n, right? So this is not time invariant, not time invariant. And the memoryless, no, because this is 2n. Only when n is 0, 2n equal to n, right? But when n is any number, you know, like n is 3, here is 6, x of 6. So you need a memory, so not memoryless. Okay, then the part C. C is 2 of x at n plus 1 plus 3 of x at n minus 1 and plus 1. So first one, is this stable? I will say yes. If input is bounded by the x, right? Input is x. If x is bounded by some value, you have bound function, you say it's a k. Then the output will be 2 of k plus 3 of k plus 1 as the bound. Get it? If x has a bound k, then the output will have 5 of that k plus 1 as the bound. So it is also bounded. So this is stable. It is stable. And the cautious, no. You have n plus 1 here. You have n plus 1 here, so it is not cautious, right? Some future value. And the linear, no. You have 1 here. This term is not linear, right? You have 1. 1 is related with x to the power 0. It is not x to 1. Linear you will only have x to some power 1, like a, right? This is x, just the first order, just x itself. It is not x squared, not x to 0. But here we have x to 0. So this is a nonlinear. It's a nonlinear. And the time invariant, I say yes. Yeah, you shifted n by some value, then here you also shifted by same n, right? So it is a time invariant. And the memoryless, no. You have n plus 1 and minus 1. It's not memoryless. Alright, so this is 1. Yeah, this is the first problem. And then the second problem. Okay, we have a function x of z. We want to find the inverse z transform of this function. Here the ROC is r smaller than 1 over 2. Okay, check the solution. I wrote the solution here. So this is x, and this is x. Then we need you want to find the inverse z transform. You can use partial fraction method, right? So you need to rewrite these so that the denominator is a multiplication of some simple factor, looks like this. And here you need to know how to write this denominator in this way. You can try like this is a negative 1 over 2. It is a -1 times +1 over 2, right? And this -1 over 2 is -1 plus +1 half. So you get this one, right? You can also try to solve it by the formula of the quadratic polynomials, the root of quadratic polynomials, right? So you both methods, you can find the denominator can be written in this way. And this is RC. Oh, RC is given, right? I put a 2 point for this RC. Anyway, then we will write these in terms look like this, right? This is partial fraction, and we will try to find this A and B. Then here's a way to solve the partial fraction. To solve this problem, we times the whole denominator in this fraction in both sides. Then we'll have this one equal to A times 1 plus half z to -1, and B times 1 minus z to -1. So we have this one, and you can choose different z values, plug in, then you can have A and B. I choose z equal to 1 or z equal to this negative 1/2. I can have A and B. Now you can have different ways. You can put the different values of z, or just compare this equation, both sides. You compare the constant terms and z -1 terms, and you can also solve the equation to find these values. But it doesn't matter which method. Finally, you will have A and B. A and B. A is 4 ninths and B is 5 ninths. 5 of ninths. Okay. Then you can go back to the time domain, right? You have A and B, then you can go back to time domain. Okay. Yeah, a little bit smaller. Like this, right? A over 1 minus z -1. And okay, I said you need to use these z smaller than 1/2. The RC, this one. The RC is this one. You should mention, because of this one, you can have these two. Okay. If this is a different RC, here will be different. Now it's smaller than 1/2, so smaller, right? Smaller. So u should be in the negative side. You can find the table. You have two ways to go back to time domain, depending on the RC. If RC is larger than that A number, here will be positive and here will be n. And if it's smaller than the number, this will be negative here, and here's a negative n minus 1. Right? This is from the table. Similar, this is also from the table. Yeah, you're done. If you want, you can make a little bit simplify. Rewrite these. You put the negative in front, then 4 over 9 times u of negative n minus 1. And this is negative 5 over 9 times negative half to the n times u to negative n minus 1. Here, you should know, you cannot remove this -1 in front, because the power is a power, right? When n is odd, you have negative, but when n is even, this after the power, here is a positive, right? So you cannot just remove it, because this sometimes positive, sometimes negative. You can move it in front. Alright, that's it. So this is just the problem. Try to find the inverse z transform. Inverse z transform. Okay. Then go to the third problem. Here we have a frequency response of LTI system, and we have an input. So here we have 4 questions, A, B, C, D. Let's go over them step by step. First one, we are asking for what is the frequency omega 0 of x of n. You see, x of n is a sinusoid, and you have some value times n and minus another value, right? So here we have 2 constant and 1 time n. So the value before n, that is a frequency, right? So here omega 0 is just that 1/3 times pi. So this is omega 0. And another negative 1/3 pi, that is a phase angle, right? Okay. Then B, find the value of the frequency h at omega equal to omega 0. Then you just plug in and do calculation. Now, of course, this kind of calculation is in complex numbers, right? About complex numbers. So you need to work like this. First of all, you need to know this e to the negative j omega 0. What is the meaning of it? By Euler formula. Actually, it's a definition of it. It is a cosine of that angle plus j times sine of that angle. The angle is negative omega 0. Right? And the second term is similar. It is cosine of that negative 2 omega 0 and j times sine of negative 2 omega 0. Right? And the denominator are similar. 2 is still 2, but this one, it is a cosine of negative 3 omega 0. Right? Omega 0 is 1/3 of pi, times 3 is just pi. So this is negative pi. Right? And plus j times sine negative pi. Then you should know what are the values cosine of negative 1/3 pi, sine of negative 1/3 pi. You plug in the values here, the value of those cosine and sine, right? Then you do some calculation. And here actually we have something can be cancelled. Like the numerator, I have half minus the square root 3 times j. And the negative 1/2 minus 3 square root of 3 over 2 times j. And here subtract. By this subtract, the j terms, these two, they will be cancelled, right? Yeah, they cancel. So we have 1/2 minus negative 1/2. That's a plus 1/2, right? Minus negative 1/2. The plus 1/2. So half plus half, get 1. And denominator is 1. This cosine negative pi is negative 1, and sine negative pi is 0. So here is 2 minus negative 1, you get 3. So it's 1/3. Okay, you have h, this capital H, when omega is omega 0, you get 1/3. Then C, find the magnitude and phase of this number. So this is the case, this is a real number, so magnitude, it is just itself, the angle is 0. Angle is 0. Right? This real number. In the complex plane, you will see it looks like this. Oh, this is too late. Give me a minute. Okay. That's 1/3, right? 1/3. 1/3 in the complex plane, it will be here. Suppose this is 1, then this will be 1/3, right? This point. Then what is the magnitude? Magnitude is the distance from this number to original point. So this is the magnitude equal to 1/3. And angle? Angle is here. Right? Angle is here. So it's 0 degree. 0 degree. Yeah, so for any complex number, for example, you have like this is half, this is a 1, and this is a 1/2 plus j. Then you can check the angle will be here, right? Angle will be here, and the magnitude will be here. This is the magnitude, this is the angle, right? Now the magnitude is 1/3, angle is 0. We have magnitude is 1/3 and angle is 0. Then last question, y of n. What is the output? Actually, the whole problem is just working on how to find the output. When input is a sinusoid, how to find the output. Of course, you can use some other early method, like you can use convolution. You try to find the impulse response, then convolution with x, you can find y of n. Right? It works, right? But need a lot of work. You need inverse Fourier transform to find the impulse response, and then convolution with x. Another way is you find the Fourier transform of x, that is capital X times h, you get capital Y, and then capital Y do inverse Z transform, or inverse Fourier transform, you get Y of n, right? It's this way. Yeah. But now we use this way. We just find the frequency and calculate the value of frequency response and determine the magnitude and the phase angle. Then we find output. Actually, this is a shortcut to find the output when input is a sinusoid. The output will be what? The magnitude 1/3 times the input signal, and inside the input signal you need to add the phase angle. So it is just this one. Just this one. Now this phase angle is 0, so you can't see it in the output. It is just 1/3 times the input. Alright. Okay, so this is problem 3. Now let's go to the last one. We have a system. This is problem 4. We have system satisfied equation. This is the equation, and we need to determine all the possible homogeneous response of the system. Then apply Z transform to find the particular solution when input is this one. Okay, and okay, because you use Z transform, you should know what is ROC. What is ROC? Here I said you can choose any one if there are several different possible of the ROCs. And okay, now with the same input, determine output if we have initial condition. We have initial condition like this. Alright. Okay, so we just solve it step by step. First one, for the homogeneous equation. Homogeneous equation is just use those terms in the original equation, those y terms in the original equation, then equal to 0. Replace all the x terms with 0. So we have just this one, right? The same with the left side of the original equation in the left side, and it is 0 in the right side. How to solve it? You just let yn is a power of some lambda and try to find this lambda. So you plug in y of n now is lambda to n. Y of n minus 1 is lambda to n minus 1. Y of n minus 2 is lambda to the n minus 2. And we can make this last term to be constant. So I just times the lambda with 2 minus n, the reverse of this power, right? Times lambda to 2 minus n. Then we times these on the equation. The last term will turn to be 1/2, and the middle term you multiply this here. This is negative n, this is n, they cancel. It's 2 minus 1, so lambda to 2 minus 1. 2 minus 1 is 1, so it's lambda. This is 1/2 times lambda with a negative, and the lambda n times these. The n and the n cancel. You have a lambda squared. Right? You multiply these two. The n and the n cancel, right? This is negative n, this is positive n, they cancel. So you only have left lambda 2, lambda squared. Okay, you have this one, then you can solve it. You can by observe or use the formula, and finally you can have lambda equal to 1 or negative 1/2. Okay, then the output will be alpha 1 times lambda 1 to some n, and alpha 2 times lambda 2 to some n. And here the special case is 1 to the n, right? I have 1 to the n, just 1, so I can rewrite it in this way. It's simpler than the first line, right? Here alpha 1, alpha 2, they could be any numbers. Yeah, this is also, you have a lot of different choice. Yeah. Okay, this is A. Then part B. apply Z transform to find a particular solution when input is this one. And also you need to indicate what is RC. Okay, so now the output, this is transfer function times input, and the input is given, is this one. So in the time domain is 1 over 1/3 times Z to negative 1, right? It should be 1 minus A, and A is negative 1/3, right? So it's 1 minus negative 1/3, so 1 plus 1/3 times Z to negative 1. And what is RC? For this X, the RC is larger than 1/3. Okay, then you times them together. You see, this transfer function has 1 plus 1/3 times Z to negative 1, this term, at the numerator. And the capital X of Z has the same term in denominator, so they can be cancelled, right? This one and then this one, they can be cancelled. So after you times X on this transfer function, the numerator term and this term, they are cancelled, right? So we only have 1 over this. Okay, then I rewrite it in this way. And what is RC? Okay, so here you can use RC Z larger than 1 or smaller than 1, or smaller than 1/2 is also fine. Smaller than half or between 1/2 and 1. Right? You can choose these three, any one is fine. But here I choose these in this solution, and I don't know what you did in your exam papers. That all of them, any one, it works. Okay, so now I just follow this. Use Z larger than 1 as RC. And then we need to find Yn by inverse Z transform. So partial fraction, right? Partial fraction. Y equal to A over these plus B over these, or equal to this one. Then I times the denominator on both sides. I have 1 equal to A times 1/2 Z to negative 1, and plus B times 1 minus Z to negative 1. And I pick some special values for Z and solve it. I can get A and B. 2/3 and 1/3, they're A and B. Then I just plug A and B here, and A is 2/3 and B is 1/3, and I go back to time domain. Notice that RC is larger than 1, so here's U of n. If we use RC is smaller than some number, smaller than 1/2 should be, then here will be U of negative n minus 1, and in front you need a negative value, right? That will be different. But here I use RC is Z larger than 1, so it is this one's output. This is output. Okay, so this is a particular solution. Different RC gives different YP. This is the part B. And part C. Now we have a particular solution and homogeneous solution, so the overall solution will be combined of these two. Of course, in this combination we have two values. They are uncertain, alpha 1 and alpha 2. They could be any values. Now we will use the initial condition to determine that those two uncertain values, alpha 1 and alpha 2, right? So here initial condition is given here. When n equal to 0 and negative 1, the value of y will be 1. Okay, so it's just this, right? This one, when n is negative 1, it is 1. And when n is 0, it is also 1. Then we plug in what is yp. Yp is here. So you plug in this one with n is negative 1, you get 0 because you have un, right? Un. When n is negative 1, both u of n, they are zeros. So there is a 0. And plus YH. YH is alpha 1 plus alpha 2 times negative 1/2, and here is a power n. Now n is negative 1, right? So this is the first equation. And the second equation, now n is 0. You plug in 0 here, n is 0 here, you get 2/3 plus 1/3, you get 1. Yeah, 2/3 plus 1/3, this should be 1. And for the second part, homogeneous solution is here. So alpha 1 plus alpha 2 with negative half to the n. So here will be alpha 1 plus alpha 2 with negative half with power n. Now n is 0 equal to 1. Okay, so initial condition, these two initial condition, we get these two equations. Unknown are alphas. Okay, to some simplify, alpha 1 is alpha 1. This term, this is a negative 1/2 with power negative 1, we get negative 2. So it is negative 2 times alpha 2 equal to 1. Second equation here, 2/3 and 1/3, you add them together, you get 1. And here is also 1, so they cancel. The result will be alpha 1 plus alpha 2 equal to 0. Right? This is alpha 2 because the power to 0 is 1. Alpha 2 times 1 is alpha 2. So alpha 1 plus alpha 2 equal to 0. Okay, then we solve it. Alpha 1 plus alpha 2 is 0, so alpha 1 is negative alpha 2. Then plug in here, alpha 1 is negative alpha 2 minus 2 alpha 2 equal to 1. So we have negative 3 of alpha 2 equal to 1. So alpha 2 is negative 1 over 3. Now when you have alpha 2, alpha 1 will be negative alpha 2, negative of alpha 2. So alpha 1 will be positive 1/3. Then we just plug in. What is y? It will be, let me see, the first two terms. This is coming from the particular solution. And the second term, we have alpha 1 is 1/3, and alpha 2 is negative 1/3, and times negative 1/2 to the n. Alright, so this is the answer of part C. Answer of part C. Okay, this is problem 4. Okay, that's all. We have 4 problems. Alright. Okay, if you have any questions regarding these problems, you can leave a message in the Piazza or visit my office hour later, right? Next week we will go back to the normal office hour, and also we can discuss during the class, before or after the class, right? This Friday I will go back to the class. Yeah, I think I will. Yeah, and actually I will give announcement when I have the schedule. Yeah, when I have the schedule I will give you announcement to tell you, okay, like Friday I will go back. Yeah, I think I can go back. Yeah. Okay, then see you next time. Bye bye. Have a good day. Oh, I have 32. Only have, yeah, it's fine.